We are moving now into our second presentation. The title is Decarbonization with Fiber Reinforced Polymer Composites. It's given by Dr. Joe Fox, President of FX Consulting, LLC, a consulting firm for the specialty chemicals and materials industries based in Dublin, Ohio. Joe has a PhD in chemistry from Penn State and is a 40-year veteran of the chemicals industry, having worked at Standard Oil of Ohio, BP America, Ashland Performance Materials, and Ineos Composites. I like Ineos because it's sponsoring a team in the Tour de France. You may have seen that. He's an active member of the American Composites Manufacturers Association, ACMA, the Society for the Advancement of Materials and Process Engineering, SAMPE, and the American Society of Civil Engineers, ASCE. He's currently co-facilitator of the Infrastructure and Construction Working Group for the Institute for Advanced Composites Manufacturing Innovation, IACME. And in this role, we have been working closely with Joe, and it has been really a pleasure to have him here a number of times. And we welcome now Joe to the podium.
Thank you, Roberto. It's always a pleasure to come back here. And it's a pleasure to be able to talk to you about decarbonization with fiber reinforced polymer composites. And John is a tough act to follow. All right. It's fair to say that decarbonization is a hot topic these days. It's an important part of a bigger conversation on sustainability. But it's very clear that the federal government wants to lower greenhouse gas emissions, or GHGs. They want to decarbonize many different industries, and the Department of Energy has put together a decarbonization roadmap outlining how to do that. Also, the government is putting a lot of money, billions of dollars in grant money, where their mouth is, because the Inflation Reduction Act provides grants for the use of low carbon materials in construction of buildings, and $2 billion with a B for infrastructure. And one of the Department of Transportation's current Everyday Counts, or EDC7 initiatives, is focused on reducing greenhouse gas emissions from infrastructure projects. That's hard to get used to. So with that background, here's an outline of my talk. I'm going to give you a little bit more terminology. Then I'm going to tell you about some sources of data for embodied carbon calculations. Then I'm going to show you some examples of both lower cradle-to-gate and cradle-to-grave CO2 emissions with composites. I'm going to give you my take-home message now and then repeat it at the end of my talk. My take-home message is that the use of FRP composites can lower embodied carbon and CO2 emissions in construction and infrastructure applications. It's a very simple message, but I hope you'll see it's true for both cradle-to-gate and cradle-to-grave emissions as I go through the rest of my talk. So people say they want to decarbonize, but different people say it in different ways. Some people say that they want to lower their carbon footprint. Others say they want to lower greenhouse gas or GHG emissions. Still others would say, I want to lower embodied carbon. The point that I want to make is that all these statements are saying essentially the same thing. Everybody wants to lower emissions of carbon dioxide. So this is a great slide for understanding embodied carbon. And I want to acknowledge Connor Usry from RMI and the Advanced Building Construction Collaborative, or ABCC, for letting me use it. The reason I like it is because the definitions are simple and easy to understand, especially when you look at this flow chart right here. Let's start with cradle-to-grave and embodied carbon. Embodied carbon refers to the greenhouse gas emissions associated with the manufacturing, transportation, installation, maintenance, and disposal of building materials. As seen in the flow chart here, it goes from cradle to grave, all the way from manufacturing to disposal. And then there is upfront embodied carbon, or cradle-to-gate emissions, which focuses on the greenhouse gas emissions released before a building or another structure is constructed. These are also referred to as supply chain emissions or product stage emissions. Again, they are the upfront embodied carbon, the upfront cradle-to-gate emissions. little bit more terminology. Everyone wants to lower carbon dioxide because it is the most abundant greenhouse gas, but it is not the only greenhouse gas. Gases like methane and nitric oxide are also greenhouse gases, and each of those gases has what's called a global warming potential, or GWP. And that GWP is used to calculate equivalents of CO2 emissions. And the most common unit is kilograms of CO2 equivalents, and you will see this acronym, kilograms CO2e, 4 kilograms of CO2 equivalents, and you'll see it repeatedly during the rest of my talk. So now let's talk about some sources of embodied carbon calculations, sources of data. I'm going to talk about 3 different sources, and I want to warn you in advance that this slide has a lot of acronyms on it. The first is this database, this Material Baselines database from the Carbon Leadership Forum. I call it the CLF Database. The second is this life cycle inventory from ACMA, the American Composite Manufacturers Association. And the third is this Environmental Product Declaration, or EPD, for FRP Rebar. So lots of acronyms. Let me walk you through each of these. So first, you've got the CLF database, the Carbon Leadership Forum database. This contains embodied carbon data for a whole host of building materials, and including the ones shown here for various types of steel. The data is given in kilograms of CO2 equivalents, and it's given 3 different levels: achievable, typical, and baseline. I'm going to highlight the one with the star here because I'm going to use this steel data in the FRP rebar, or the emissions calculations that I show you in just a short time. I also want to make the point before I leave here that it's very important to watch the units when you're going through this database, because this data for steel is given in kilograms of CO2 equivalents per kilogram. But if you look at the data for concrete, it's in kilograms of CO2 equivalents per cubic meter. A little bit more about the scope of the CLF database, and this comes right from their description of their database. The CLF Baselines report gives you product stage carbon impacts, or cradle-to-gate impacts. And they point out here that these emissions comprise the majority of embodied carbon impacts for the majority of materials. And if anyone would like a copy of this database, you can send me an email after the fact, and I will send you a copy of this database. Now let's look at some source data for FRP composites. And here we're looking at the life cycle inventory from ACMA. Again, this is Cradle-to-Gate, which is the same as the CLF database. And this database contains embodied carbon data for unsaturated polyester resins and e-glass. It also contains data for composites prepared by different fabrication methods. This version is from 2012, and it is being updated as part of ACMA's Climate Impacts Project, which was launched last year. Here's the type of data that appears in ACMA's LCI. Here is, again, you're talking about cradle-to-gate data. Here's the cradle-to-date emissions data for vacuum-infused composites. I'm going to use it for the FRP Girder calculations in just a little bit. And here is the data for open molded composites, which are going to be used for the grading calculations that I'll show you. Again, if anyone would like a copy of this LCI, email me after the fact. And finally, we get to environmental product declarations, or EPDs. These are also typically cradle-to-gate. They do contain, some of them do contain emissions data for downstream emissions. I have found that buildingtransparency.org is a very useful resource for EPDs. Here I'm showing you the EPD for FRP Rebar from Schock, a German company, and I'm going to use the data in it for the rebar calculations shortly. Here are some of the emissions data from that EPD. I'm going to highlight 2 sections of this table. At the top, you've got a description of the different stages, and what we're focused on here is the product stage that I have defined earlier. That's the same as the CLF database for steel. And then you've got the emissions data for that, for the product stage. And this is in kilograms of CO2 equivalents. And I'm going to use this data for the rebar calculations. So the point that I want to make is that I've shown you 3 different data sources, but using data from these 3 sources enables apples to apples cradle to gate comparisons. So now let's show some comparisons, some calculations for cradle to gate. I'm going to show you 3 different comparisons. I'm going to compare FRP and steel rebar, FRP and steel girders, and FRP and steel gratings. Again, cradle to gate. So let's talk about FRP rebar. John talked quite a bit about it in his talk. It can be used as a replacement for concrete. It's used in all kinds of buildings and bridges and seawalls. It is 72% lighter than steel rebar and much more corrosion resistant. But when you use FRP rebar, you need to use 20% more on a lineal foot basis relative to a steel to achieve the same stiffness. And that's per Steve Nolan from the Florida DOT, who I want to acknowledge here, and then I'll mention later when I talk about the Halls River Bridge LCA. So now let's do some math. What I'm comparing here is steel rebar versus FRP rebar. And for the steel rebar, this column contains the source data. I'm using the CLF database. And remember that there are 3 different levels given. Here are those values for kilograms of CO2 equivalent per kilogram. To keep the math simple, I've made it weigh 1,000 kilograms. And this column is simply the product of these 2 columns. Then I come down here for FRP rebar. And now I'm using the data from the shock EPD. When I calculate the weight, this number reflects the fact that FRP is 72% lighter, but that you need 20% more. And when you take this product, you get 739, which is much lower than the values higher up in this column. And when you do the math, this new column shows the percent reduction that is possible with FRP. And the data shows that CO2 emissions are at least 8% lower with FRP rebar, 25% lower than per typical steel rebar. Next, let's talk about FRP girders. And I think many people in the audience are familiar with these, so I'll go through it pretty quickly, and Bill's going to talk about it. Technology developed by the University of Maine, commercialized by AIT. The girders are typically prepared by infusion with vinyl ester resins. They are 70% lighter than steel girders, making them much easier to transport and install, and they are much more corrosion resistant than steel. Let's do some more math. Again, now I'm using the steel data from the CLF database for plate steel, 3 different values. For the FRP girder, I use data from ACMA's LCI for vacuum infused composites, which I showed you earlier. But I have to make one assumption, because that life cycle inventory does not contain data for unsaturated polyester resin or for vinyl ester resins. So I have to use the data for unsaturated polyester resins as a surrogate. As a chemist, I'm perfectly fine with that assumption. Again, FRP is 70% lighter. You do the math, and this new column shows you even more impressive reductions in FRP relative to steel. It shows you that CO2 emissions are at least 21% lower with FRP girders, 46% lower than for a typical steel girder. One last example. Here I'm going to be talking about gratings, deckings, and railings. These type of products are produced by numerous fabricators, people like Strongwell and Amoco Seasafe. They are used in the oil and gas industry for offshore drilling. They are used in wastewater treatment plants. And they're also used by the U.S. Army Corps of Engineers for inland waterways. This is a portion of a slide presented by Eric Johnson from the Corps at the recent ACMA Pultrusion Conference. Now he's showing here railings and ladders that are used in inland waterways. It's not for bridges, but many bridges do have railings and ladders and gratings. Again, these gratings and decking are 73% lighter than their steel counterparts, and they are much more corrosion resistant than steel, which is important when you look at the highly corrosive environments that they're being used in. We'll do the math one more time. Now for the steel decking, I'm using data from the CLF database, 3 different levels. I come down here to the LCI from ASCMA, and I use the data for open molded composites, which is the way that Amoco C-Safe produces their gratings. Again, you do the math. FRP is 73% lighter. You get that 739. And the percent reductions with FRP are the highest yet. You've got at least 37% lower with FRP, 60% lower than for a typical steel grating. So to summarize the 3 examples, here is the percent reduction possible with FRP versus steel. For rebar, you're from 8 to 57%, girders 21 to 74%, gratings 37 to 70%. The bottom line from this data is that FRP has a very good cradle-to-gate decarbonization story to tell relative to steel. So far we've talked about cradle-to-gate, 3 different examples. Now we're going to talk about cradle-to-grave. And to do that, I'm going to show you data from the life cycle assessment, or LCA, that has been conducted for the Halls River Bridge. Here's a picture of that bridge. It is located in Florida, north of Tampa. It's 186 feet long with 5 spans, completed in November of 2019. This is an article from Advances in Civil Engineering Materials. The authors include Thomas Cadenazzi from the University of Miami, Professor Tony Nanni, who was Thomas's PhD advisor at Miami, and Steve Nolan from the Florida DOT. They have conducted a life cycle assessment, LCA, and a life cycle cost assessment, LCCA, for the Halls River Bridge. This is by far, the most detailed, most comprehensive LCA and LCCA I have seen for FRP in an infrastructure application. I could spend 2 hours just going through this paper, but here's the Cliff Notes version. Their LCCA showed that the net present value of the life cycle cost is 20% lower with FRP because of reduced maintenance and replacement costs. That's a good story for FRP. That's a story for a different day. Relevant today is that their LCA showed that cradle-to-grave emissions were 26% lower with FRP than with steel. And here's the data that shows that. The table at the top contains the emissions data in kilograms of CO2 equivalents for the bridge with FRP elements versus the one with steel elements. And if you compare this data point with this data point, you will see that the emissions are 26% lower with FRP than with steel. And they are lower at every stage in the process. Now, if Thomas Cadenazzi were here and we had more time, he would show you this collage of slides. They are taken from a presentation in an ACMA webinar that Thomas and I gave earlier this year. And in these slides, he shows for each step in the process how FRP is lower than steel: product stage, transportation, construction, use, replacement, end of life. And again, the bottom line is that the kilograms of CO2 equivalents are 26% lower with FRP than with steel, and they are lower at every stage. So I'm going to finish up with my take-home message one last time, that the use of FRP composites can lower embodied carbon and CO2 emissions in construction and infrastructure applications. I've shown you 3 examples for cradle-to-gate, where the emissions were 8 to 74% lower, and the Halls River Bridge analysis showed you that for cradle-to-grave, 26% lower with FRP than with steel. And so the final take-home message is, if you want to decarbonize, if you want to lower embodied carbon, if you want to lower carbon dioxide emissions, you need to be considering FRP. And that concludes my presentation. I'll be happy to answer any questions during the panel.